Good day, everyone, and welcome back. Today we'll be taking a look at the Cambridge International AS and A-Level Chemistry Paper 4. That's 9701, Paper 42 for the October-November 2022 exam series. Now, as some background information for this paper, these were the grade boundaries for the A, B, C, D, and E grades for this paper. And this is out of 100. So we can see here for A on this paper, you needed to get 57 out of 100 minimum. So if you're getting 60s, 70s, 80s, and more in your exams, you should be in really good condition. So let's jump straight into this paper. So question 1 starts off with calcium chloride as an ionic solid, and the values of some of the energy changes are given in this table. And for 1 mark, they ask us to define lattice energy. So what is the lattice energy? Lattice energy is the heat change, or you could say the heat evolved, because lattice energy is always exothermic. So you can say the heat evolved when 1 mole, and this is important, 1 mole of an ionic species is formed from its gaseous ions. So is formed from its gaseous ions. So this is the important part of the definition. It's the heat change or the heat evolved when 1 mole of an ionic species is formed from its gaseous ions. 1 mark. Now, if the question had asked you to define the standard enthalpy of lattice energy, you would have to additionally include that it is the standard conditions will be applied. So it will be the heat change or heat evolved when 1 mole of an ionic species is formed from its gaseous ions under standard conditions, which would be 298 Kelvin, 1 atmosphere. Right? That is if they had asked you for the standard enthalpy change of lattice energy, or something like that. In this case, they're just asking for lattice energy, so we don't need to mention the standard conditions. So pretty straightforward there. Then the question goes on, use the data in table 1.1 to calculate the standard enthalpy change of formation of calcium chloride. It may be helpful to draw an energy cycle, show all your working. So what we need to do here is construct perhaps a Born-Haber cycle for the formation of calcium chloride. And a Born-Haber cycle is pretty straightforward. Always do the metal and the non-metal in turn. What do I mean? If we have to draw an energy cycle, a potential energy cycle could look like this. We start off with our metal. So we have calcium solid and we have Cl2 gas. We start off with our metal first. So we atomize our metal and we'll get calcium gas and chlorine gas. Then we ionize our metal. So calcium will form calcium 2+. So that we'll have to do the first and second ionization energies. So delta H first IE, second IE. So we'll get Ca2 plus gas plus Cl2 gas. And then what we do, we atomize the non-metal. And this will give us Ca2 plus gas and 2Cl gas. After we reach this point, we then have to do the electron affinities. So it's like almost the reverse of ionization energy. We do the electron affinities for chlorine, and this will be the first electron affinity for chlorine, and this value will have to be multiplied by 2. Since we have 2 chlorine atoms, this will give us Ca2 plus gas plus 2Cl minus gas. And then we have our lattice energy of calcium chloride, which will give us CaCl2 solid, and then this value here is the formation enthalpy. And from Hess's law, this formation value is the sum of all the individual steps. So if we go back now to our table, we can see that our atomization value for the calcium is positive 193. So this would be positive 193. Then we do the first and second ionization energies of calcium, which is positive 590 and positive 1150. So positive 590 plus 1150. Then we do the atomization of the chlorine. Now, this is important. Atomization enthalpy is the heat change when 1 mole of gaseous atoms is formed from its elements. Now, if we look at the case for chlorine, we are actually forming 2 moles of chlorine atoms. Therefore, the atomization value that they have given to us here, positive 121, has to be multiplied by 2. This is important because it stems from what the definition of atomization enthalpy is. It is per 1 mole of atoms. And we have 2 here, so we multiply by 2. As already mentioned, the value for the first electron affinity of chlorine is negative 364, and we need to multiply this value by 2 since we have 2 chlorine atoms. The lattice energy is negative 2237. And if we add all of these together, so positive 193 plus 590 plus 1150 plus 121 by 2 plus negative 364 by 2 plus negative 2237, this gives us the value of the formation enthalpy, and we should work out an answer of negative 790 kilojoules per mole. And again, these Born-Haber cycles are pretty standard, pretty straightforward. Always treat your metal and non-metal separately. So you first atomize your metal, ionize your metal, and then you shift to your non-metal. You atomize your metal, you do the various electron affinities of the non-metal, and then you do your lattice energy, and the difference will give you the formation enthalpy. Right? Pretty straightforward. Part C of the question tells us that 3 possible values for the first electron affinity of bromine are shown in table 1.2. One of them is correct. Place a tick by the correct value and explain your choice. And we are comparing this against chlorine. So they tell us here the first electron affinity of chlorine is negative 364. So the question becomes, would the electron affinity of bromine be greater or less than chlorine? And the answer is, it will be less. It will be negative 342 kilojoules per mole. And the answer is because of the atomic radius. Chlorine is a much smaller atom than bromine because bromine has an extra quantum shell. So what actually happens is the bromine atom is larger than chlorine. And what does this mean? It means that the nuclear attraction for an incoming electron or for an inbound electron is less in bromine. Therefore, the reaction is less exothermic. And this idea of the nuclear attraction for an inbound electron has to do with the electronegativity. The electronegativity of bromine is less than chlorine. And this stems from the fact that bromine is a larger atom than chlorine. Hence, the electron affinity value of bromine should be less exothermic, that is less negative, than the chlorine value. So then we move on to part D. They tell us the enthalpy change of hydration of the chloride ion can be calculated using the lattice energy of calcium chloride and the data shown in table 1.3. So we have our data here. They ask us to define some terms. So the enthalpy change of solution. So the enthalpy change of solution is the heat change when 1 mole, again, 1 mole of a species dissolves in water to form an infinitely dilute solution. An infinitely dilute solution. Now, I use the term heat change because enthalpy change of solution could be exothermic or endothermic, unlike, for instance, say lattice energy, which is always exothermic. Right? And then we look at the enthalpy change of hydration. The enthalpy change of hydration would be the heat change, or you could say the heat evolved, because hydration enthalpies are always exothermic. When 1 mole of gaseous ions dissolve in water. Right? So these are the definitions here. For enthalpy change of hydration, we are looking at gaseous ions dissolving in water. Enthalpy change of solution, we are looking at 1 mole of a species dissolving in water. Right? And then for part 2, they say calculate the standard enthalpy change of hydration of the chloride ion. It may be helpful to draw an energy cycle. So again, like before, we need to construct a Born-Haber cycle here for the dissolving of an ionic compound. So the cycle would look something like this. We have solid calcium chloride, and what we do, reverse lattice energy to give calcium gas and chloride gas, and then we do the hydration energies. So this is the hydration energy of Ca2 plus and the hydration energy of Cl minus gas, and then this gives us here CaCl2 aqueous, and this difference here is our enthalpy change of solution. So if we put values into this, the reverse lattice energy, now our lattice energy value from before was negative 2237. So if we do the reverse lattice energy, that is splitting up the compound from the ionic solid into the gaseous atoms, ions, it will be an endothermic process. So we reverse the sign on the lattice energy as the name suggests, and we will get positive 2237. So this is positive 2237. We know what the enthalpy change of hydration of the calcium ion is. So this plus negative 1650 plus 2 times the hydration value of Cl minus gas, and we can be algebraic here and call that X, must be equal to the solution enthalpy, which is negative 83. And all what is required for us to do here is to algebraically solve for X, and you should get that X is negative 335 kilojoules per mole. So negative 335 kilojoules per mole. A good way to check back your answer as well. You know it's a negative answer, so you're on the right track. Again, because hydration enthalpies are always exothermic. And of course, the reason why we multiply by 2 is because we have 2 moles or 2 ions of Cl minus that are hydrating to form the aqueous solution. Right? So that is part 2. Part E tells us that calcium fluoride can be synthesized directly from its elements. The value of the enthalpy change of formation of calcium fluoride is negative 1214 kilojoules per mole. Predict the sign of the entropy change for this synthesis. Explain your answer. So they say calcium chloride can be synthesized directly from its elements. So it means we are taking calcium solid and fluorine gas and forming calcium fluoride, which is a solid. We should see here that the number of moles of gas is decreasing in this reaction. So we should expect the sign of the entropic change to be negative. Right? Remember, a positive entropic change is usually associated where we have increasing disorder or randomness in the system. And we know that gases have higher entropies than solids or liquids. Because the number of moles of gas molecules is decreasing in this reaction, so number of moles of gas molecules are decreasing, we expect a negative entropic change. Right? And then part 2 says, use the value of the formation enthalpy given in E and your answer in E1 to predict how the feasibility for this synthesis will change with increasing temperature. So when we talk about reaction feasibility, we of course have to make mention of delta G. So delta G is given by delta H minus T delta S. For a reaction to be feasible or for a reaction to be spontaneous, delta G has to be less than 0. So delta G must be negative. Now, we have just indicated that delta S is positive. And we also see here that delta H is negative. So the first term is negative. And what happens is that our second term is, if we consider negative T delta S, this term negative T delta S is actually a positive value, because delta S is negative and minus T makes it positive. So we have a negative enthalpic change and a positive negative T delta S term. If temperature gets larger, so if temperature increases, the T term in this expression will get larger. So this second term will get more and more positive, right? So this second term will get more positive. And as this gets more positive, it means that our overall result, if we have a negative number and we are adding it to a positive number, the overall result will get more and more positive. So delta G actually gets more positive. Delta G gets more positive. Therefore, the reaction feasibility decreases as temperature increases, right? And typically, this is how we answer and treat with questions involving feasibility of reactions by consideration of the effect of temperature on delta G, where you treat the delta H and the T delta S terms and consider the combined effect together to see if delta G is getting more positive or less positive, right? And that was question 1. So moving on to question 2, it tells us here that nitrogen monoxide NO reacts with ozone O3. This reaction is first order with respect to both NO and O3. At 298 Kelvin, the rate constant K is 11,500 mole to the minus 1 dm cubed S to the minus 1. So the first part is to complete the rate equation for this reaction. So the question tells us it's first order with respect to both NO and O2. So the rate is given by the rate constant K times NO by O3, O3, right? And it's first order, so the power is 1, right? Now they say a reaction is carried out in which the initial concentrations of NO and O3 are both 1.2 by 10 to the minus 6 mole per cubic decimeters. Calculate the initial rate of this reaction, state the units. So the rate of the reaction is simply obtained by substituting in the values of the rate constant and the concentrations into the rate law that we just obtained. So the rate will be equal to 11,500 times 1.20 by 10 to the minus 6 by 1.20 by 10 to the minus 6. And this should give you 1.656 by 10 to the minus 8. Or we can say 1.66 to 3 significant figures. And what are our units? So we have essentially the rate constant term is mole to the minus 1 dm cubed S to the minus 1. And then this is being multiplied by essentially mole squared dm to the minus 6. And when we multiply, if this is some laws of indices here, when we multiply indices like these, once we have the same base, we simply add the exponents. So it's minus 1 plus 2 becomes 1. So we should get mole. 3 plus minus 6 becomes minus 3. So we get dm to the minus 3. And then we get S to the minus 1. And those are our units, right? Part 3 asks us, the reaction described in A2 is monitored over a period of time. Predict whether or not the graph of NO against time under these conditions shows that the reaction has a constant half-life. Explain your answer. Now, what does it mean if there's a constant half-life? What does that imply? A constant half-life is indicative of a first-order reaction, right? A first-order reaction will have a constant half-life. Now, it may be easy to get tempted here to think that because the reaction is first order with respect to NO, you should get a reaction that shows you a constant half-life. However, this idea only holds when we are considering the overall reaction order. The overall reaction order here is 2. Therefore, you will not get a constant half-life, right? So that is important to recognize. You will not get a constant half-life because the reaction is not first order overall. If it was an overall first order reaction, as in the rate of O3, the concentration of O3 had no effect on the rate, then you could say that you would get a constant half-life. But that is not the case here because the reaction is not first order overall. Right? Then we continue to part B. Nitrous oxide N2O decomposes into its elements. At a high temperature, a small amount of platinum wire is added to a large amount of nitrous oxide. The reaction follows zero-order kinetics. The platinum wire behaves as a catalyst. Sketch a graph on the axis below of reaction rate against time for the catalyzed decomposition of N2O under these conditions. Now, if the reaction follows zero order kinetics, it means therefore that the concentration of the N2O has no effect on the rate of the reaction, which means therefore that our reaction rate will be constant, and a constant reaction rate would be seen by a straight line like this, a horizontal line like this. There's a constant reaction rate with respect to time, which would indicate a zero order, right? And then they ask us to sketch a graph on the axis below of the concentration of N2O against time. And you should also recall that for a zero order reaction, because there's a constant rate of reaction, there is a constant decrease like this with respect to time. So this is what our graph would look like here. All right? So hopefully pretty standard questions there. Then part 3, platinum behaves as a heterogeneous catalyst in this reaction. Describe the mode of action of a heterogeneous catalyst. Generally, there are 5 steps to how a heterogeneous catalyst behaves. There's diffusion. So the first step is that the reactants diffuse to the catalyst surface, right? Then there is adsorption, not absorption, adsorption of the reactants to the surface. And this absorption is such that it leads to a weakening of bonds in the reactants, right? So there's diffusion, adsorption, which leads to a weakening of the bonds. Then there is reaction occurs. Then you have desorption of the product and any unreacted material from the catalyst surface. So desorption from catalyst surface, and then finally you have diffusion away from the surface. Right? And generally this is how you would describe the mode of action of a heterogeneous catalyst, right? There's diffusion of the reactants to the catalyst surface. It is then adsorbed to the surface of the catalyst. This adsorption is such that it weakens the bonds in the reactants, but the interaction, the adsorption, the force of that interaction is not so strong that after the reaction, the molecules cannot leave, right? So there's an attraction of the molecules to the surface sufficient to weaken the bonds, but not so great that after the reaction occurs, they cannot leave the surface. So once you weaken the bonds, the reaction occurs, then you have desorption from the catalyst surface, and then diffusion away from the surface, diffusion of products and unreacted material. Right? And that is how the heterogeneous catalyst works. And then the question says, suggest a reason why this reaction has zero order kinetics when the amount of nitrous oxide is large and the amount of platinum is small. So, and this is important, we have a very large amount of nitrous oxide. So why does the reaction show zero order kinetics? Again, zero order kinetics tells us that the concentration of the N2O is having no effect on the rate. What would actually affect the rate of this reaction would be the availability of catalytic sites. Because we have so much nitrous oxide, it means that all the catalytic sites on the platinum surface is filled. And because it's filled, the reaction would only proceed based on the interaction between the molecules and the catalyst. That is what would dictate the rate of this reaction. The concentration of the N2O has no effect, right? And that is why, because all the catalytic sites on the platinum surface is simply filled, right? So that was question number 2. Moving on to question 3, which deals with electrochemistry. We are told here that an electrochemical cell can be constructed from a magnesium 2+ magnesium half cell and a manganese half cell. The standard cell potential could be calculated using the electrode potentials of the two half cells. So the first part asks us to define the standard electrode potential, include details of the standard conditions used. So standard electrode potential is the voltage of a half cell measured under standard conditions relative to the standard hydrogen electrode, the SHE. Of course, in the exam, writes it out in words, standard hydrogen electrode. And what do we mean by standard conditions? It means that gases are at 1 atmosphere. 1 atmosphere. The temperature is 298 Kelvin, and all concentration of solutions are at 1 molar, which is 1 mole per cubic decimeter. Right? Then they say, complete the diagram below to show an electrochemical cell constructed from Mg2 plus Mg half cell and the manganate Mn2 plus half cell, and to label your diagram. So for the Mg2 plus Mg half cell, what we would have is a rod of magnesium. So let us consider this a magnesium rod connected by platinum wire to a high resistance voltmeter. This would also be a platinum wire here. So this would be your platinum wire here. Let us not forget our salt bridge. So we would label this as a high resistance voltmeter. This is platinum wire. This is also platinum wire, and this is a platinum electrode. Platinum electrode. You could also refer to it as platinized platinum or platinum black. And we have our salt bridge. So salt bridge. This is our Mg rod. And this here would be a 1 molar solution of Mg2 plus aqueous. And this here would be a 1 molar solution containing manganate ions, MnO4 minus, manganese 2 plus ions, and also H plus ions. So this is acidified. And the reason is because the half cell reaction shown here involving manganate and Mn2 plus occurs only under acidic conditions. So we need to have acid present, and all of these things need to be at 1 molar concentration. And at any point here, we need to make mention that this is 298 Kelvin, and we don't have any gases involved in this mixture, but if gases were present, it would be at 1 bar or 1 atmosphere. Right? So hopefully this makes sense, right? Now they say use a positive sign and a negative sign, identify the polarity of each of the 2 electrodes, and show the direction of electron flow. Right. So if we look at our half reactions shown here, we already identified that, so it's manganate. So my bad, I identified the wrong reaction here initially, right? So it's this, not this. So it's not this. Let's scratch this off. This is not the half reaction. This is manganate and Mn2 plus, right? So this reaction has the more positive electrode potential value. And again, how we interpret these things, the more positive the electrode potential value, the more likely it is that that species will undergo reduction. So the more positive, it means that reduction reaction will happen. And this is our magnesium value up here. Right, now looking at this, the electrode potential of the manganate Mn2 plus system is more positive. So this becomes our positive electrode, and this becomes our negative electrode. Now it means therefore that this half reaction will proceed in the forward direction as shown, with manganate being reduced to Mn2 plus. It means therefore that the magnesium will be oxidized as such to give Mg2 plus. So the magnesium is our negative electrode, the manganate system is our positive electrode. Because electrons are being lost here in the oxidation process, electron flow is from the negative to the positive electrode. So this would be our direction of electron flow. They say to calculate the cell potential for this cell. Now the cell potential is given by E reduction minus E oxidation. We already identified that the manganate cell will be reduced because it's more positive, and the magnesium cell will be oxidized because it's more negative. So it's reduced minus oxidized, which becomes positive 1.52 minus negative 2.38, which gives us positive 3.90 volts. And this is our cell potential. The question then asks us to construct an equation for the cell reaction. So looking at our two cell reactions here, we have to balance the number of electrons in the species. And you could treat it, I like to think of it as working with a simultaneous equation. You want to make the electron, you treat the electron as the variable to be eliminated, and we want to eliminate it. So we would actually multiply this magnesium reaction by 5, and you would multiply this manganate-manganese reaction by 2. And that way, the electrons are annihilated and then we add the two reactions together. Now, what is important to remember, again, is that the manganate-manganese half cell will proceed in the forward direction as shown. You have to be very mindful to reverse the direction of the magnesium half cell, because as we said, if the manganate cell is being reduced, it means the magnesium half cell has to be oxidized. So magnesium must go to form Mg2+. So if we multiply the manganate cell by 2 and the magnesium cell by 5, we should end up with a balanced reaction that reads as 2MnO4 minus plus 16H plus 5 magnesium to give 2Mn2 plus 5 Mg2 plus 8 H2O. And you know that this equation is balanced because the stoichiometry balances. You have the same number of species on both sides, and also the charge balances on both sides. So on the left hand side we have our overall 16 minus 2, we have a charge of plus 14, and on the right hand side 5 by 2 is 10 plus 2 by 2 is 4, we have a charge of plus 14. So the charges on stoichiometry balance, so our half equation is correct. Now this question says, predict how the cell reaction will change, if at all, when the solution in the Mg2+ magnesium half cell is diluted by the addition of a large volume of water. So what happens if we dilute this? So if we go back to the cell reaction here, if we dilute the solution, it means the concentration of magnesium 2+ is actually getting less, right? Now, if it's getting less, what does this mean? It means, therefore, that our electrode potential will actually, the position of equilibrium will actually shift to the left by Le Chatelier's principle. If we reduce the concentration of Mg2+, the system will behave to produce more Mg2+. So the position of equilibrium shifts to the left. The shifting of this equilibrium to the left makes this electrode potential more negative. So from negative 2.38, it may drop to negative 2.4. And if this gets more negative, it means the value of the cell potential here, this gets more negative. It means the cell potential will just increasingly get more and more positive. So the cell potential gets more positive. Now notice what the question asks for. The question asks the cell reaction. Does the cell reaction change? The answer is no. And we just explained why. The cell reaction itself will not change. The cell potential will get more positive, but the cell potential getting more positive simply means the reaction becomes more and more feasible. So the reaction as is will continue to occur. So there is no change to the cell reaction, right? No change to cell reaction, right? Instead, what will happen is that the E cell will get more positive. E cell gets more positive, and we just explained why, and you would include that in your answer as well, right? The next question here now deals with electrolysis. It says a molten magnesium salt is electrolyzed for 15 minutes by a constant current. 4.75 by 10 to the 22 magnesium atoms are produced at the cathode. Calculate the value of the current used. So we first have to work out the number of moles of magnesium that was produced. So the number of moles of magnesium produced is 4.75 by 10 to the 22 divided by Avogadro's constant L, which is at the back of the question paper in the data sheet, which is given as 6.022 by 10 to the 23. And this should give us 0.0789 moles. Now, how do we work out the current used? So, another relationship that you should be aware of is the given coulombs of charge, or the charge passed divided by the charge required to form 1 mole is equal to the number of moles of species. Now, what is the charge required to form 1 mole? Magnesium, in this electrolysis, reduction will happen at the cathode. So magnesium will pick up 2 electrons to form molten magnesium metal, right? So we have to pick up 2 electrons. So what is the charge required to form 1 mole of magnesium? It would actually be the Faraday constant times 2, which would be 96,500 by 2, which is 193,000. So the charge that we have passed in our circuit, which is IT, all over 193,000 is equal to 0.0789 moles. Therefore, IT is equal to 193,000 by 0.0789. So I is equal to this value divided by T. Now, what is T? Remember, T is measured in seconds. Therefore, this value of T will become 15 by 60. And this should give us a current of 16.9 amps. Right? And that is question number 3. Question number 4 now. So the value of the solubility product of iron 3 hydroxide is given by the following expression. Calculate the solubility of iron 3 hydroxide in water. So how would we do this? So iron 3 hydroxide, FeOH3, when it dissociates, will give us Fe3 plus 3OH minus. So if we have X moles of the hydroxide, we get X moles of iron 3 and 3X moles of the hydroxide ion. And if we substitute this into the KSP expression that we have here, it means that the KSP is equal to X times 3X cubed, which becomes 27X4. And X in this case is our molar solubility. So the value of our solubility is the KSP value divided by 27, all taken to the 4th root, which when you evaluate on your calculator, you should get 9.28 by 10 to the negative 11 moles per cubic decimeter. Right? Then we are asked to calculate the solubility of iron 3 hydroxide in a 0.01 molar solution of barium hydroxide. Now, from just looking at the question, we should know what our final value would be like. We are now dissolving the iron 3 hydroxide in a salt that has an ion in common with it. And we know that there should be a predicted reduction in solubility. So when you calculate the value now, the solubility value of iron 3 hydroxide, you should get a value less than the answer you just found here. And that would enable you to know whether you are on the right track or not. So all what is required for us to do really is to substitute into the KSP expression our values and solve for the concentration of Fe3+. Right? Now you have to be careful here. What is our concentration of hydroxide ion? This is barium hydroxide. Barium hydroxide actually forms Ba2 plus 2OH minus. So 0.01 molar barium hydroxide produces 0.01 by 2 molar hydroxide ions. So the concentration of hydroxide ions in solution would actually be 0.02 because we have 2 moles of hydroxide ions being formed. So all what is required for us to do is to just substitute in our values and solve for Fe3+. So we should get that the KSP value, which is 2 by 10 to the negative 39, so 2 by 10 to the negative 39 divided by 0.02 cubed, and this gives us the concentration of Fe3+, which we should get to be 2.5 by 10 to the negative 34 moles per cubic decimeter. And as we see, our value is significantly less than initial, which is good indication that we are on the right track. And the part 3, we already answered part 3. What accounts for this reduction in solubility? It is the common ion effect. Right, so that should be pretty straightforward so far. The question continues now. The numerical value of Ka of HBRO is 2 by 10 to the negative 9. X is a solution of HBRO which contains 4 by 10 to the minus 3 moles of HBRO in 100 cubic centimeters of solution. In this solution, the following equilibrium is established in which there are 2 conjugate acid-base pairs, right? Define conjugate acid-base pair. So a conjugate acid-base pair is simply 2 species which differ by a single H+, right? 2 species which differ by 1 H+ ion. Right, and we are asked to identify the conjugate acid-base pairs in the equations above. So remember, an acid is a proton donor, a base is a proton acceptor. So let us first consider the forward reaction. In the forward reaction, we should realize that HBRO is donating its proton to water to form BRO minus. So HBRO is actually our first acid in this pair. And BRO minus likewise will become our first base. If we look at the second pair now, we consider the reaction in reverse. In reverse, we should see that H3O plus acts as the proton donor. It donates a proton to the BRO minus to form back HBRO. So H3O plus is our acid, and in this case, water becomes our base pair. So, and these are how you identify these things. So you consider the forward reaction. HBRO donates the proton to water, right? And the species that is formed becomes the conjugate base. Likewise, H3O plus donates its proton to the bromate ion, or the BRO minus ion, and the species that is formed as water becomes the conjugate base. So that's how we work out the conjugate acid-base pair here, right? Then we are asked to calculate the pH of solution X showing all your working. So if we write the Ka expression, we should be able to show that Ka is H3O plus by BRO minus all over the concentration of HBRO. Now, we make the assumption that the concentration of BRO minus and H3O plus is the same. So this reaction could be, this equation rather, could be rewritten as Ka equals H3O plus squared all over the concentration of HBRO. So the concentration of H3O plus becomes Ka times HBRO all to the square root. And pH is the negative log of this, of the negative log of H plus, so it becomes negative log of the square root of Ka by the concentration of HBRO. And all what is required for us to do is simply substituting the values. We have all of our values given to us in the question. Ka is 2 by 10 to the minus 9. So we do that. Ka is 2 by 10 to the minus 9. And what is the concentration of HBRO minus? So this is important as well. The question said it's 4 by 10 to the minus 3 moles in 100 cubic centimeters. So the concentration of HBRO is 4 by 10 to the minus 3 all over 100 multiplied by 1,000, which is 0.04 molar. So this is the concentration of HBRO that you would use here. You just substitute everything in your calculator and you should get a pH value around 5.05. Good. Then they say a solution containing 2 by 10 to the minus 3 moles of sodium hydroxide is added to solution X. A buffer solution is formed. Calculate the pH of this buffer solution. So, what will happen? Let us take a look at our reaction. If we add hydroxide, the hydroxide ions will react with the hydroxonium ions here to form water. So we should recognize that the hydroxide ion would react with the HBRO in a 1-to-1 molar ratio. That is what would essentially happen. So if I write sodium hydroxide, will react with HBRO to form NaBRO plus H2O. This is one way to look at what will happen when we add the sodium hydroxide to this. Now, how do we work out the pH of a buffer solution? pH is equal to pKa plus log to base 10 of the concentration of the salt formed over the concentration of the acid. And this is the Henderson-Hasselbalch equation. Now, what is the concentration of our salt? So 2 by 10 to the minus 3 moles of sodium hydroxide is reacting with 4 by 10 to the minus 3 moles of HBRO. And this is in 100 cubic centimeters of solution. Right? So if we have 2 by 10 to the minus 3 moles of sodium hydroxide, and this is reacting with 4 by 10 to the minus 3 moles of HBRO, it means that we are going to form 2 by 10 to the minus 3 moles of the salt, of the bromate salt, of the BRO minus salt. It means therefore that the number of moles of acid left after the addition of the sodium hydroxide will be 4 minus 2, which is 2 by 10 to the minus 3 moles. Right? And this is occurring in, let's assume, a constant volume of 100. Let's assume the volume is constant, so the concentration isn't severely affected. What happens here is that the log term, the concentration of the salt and the concentration of the acid, this value becomes 1. You end up with log 1 when you do your substitution of your calculations, because we have 2 by 10 to the minus 3 moles of salt and 2 by 10 to the minus 3 moles of acid remaining. And from math, log of 1 is simply 0. So the pH actually becomes equal to the pKa. And the pKa is negative log of the Ka, which is 2 by 10 to the minus 9. So negative log of 2 by 10 to the minus 9 should give you 8.70, which is the pH of the resulting solution, right? And this is why the ratio of the salt to the acid becomes 1-to-1. And the log term becomes log of 1, which is simply 0. So we get the pH being equal to the pKa in this situation, for the reasons just discussed, right? So that is question number 4. Right, so now moving on to question number 5, which is concerned with transition elements. So copper is a transition element. It forms a wide variety of compounds. Define transition element, pretty straightforward. In this case, it is a D block element capable of forming one or more stable ions, this is important, stable ions with an incompletely filled d subshell or d orbital, right? D subshell or d orbital, right? So that is characteristic of transition elements. They form stable ions with incompletely filled d subshells or orbitals. We are told here that an aqueous solution of copper 2 sulfate contains this copper complex. If an excess concentrated HCl is added, a ligand exchange reaction occurs and copper chloride complex ions are formed. And they ask us to complete this table here. So the aqua complex here, this is hexaaqua copper 2. This complex ion will have octahedral geometry. with a coordination number of 6, and we want one bond angle. So we should remember that from an octahedral geometry, you could have two bond angles. You could have 90 degrees or you could have 180 degrees. And with this this copper chloride complex, it's tetrahedral, will be tetrahedral. Be mindful, it's not square planar, it's tetrahedral, coordination number 4. And because of that, it will have a bond angle of typical tetrahedral geometries, 109.5 degrees, right? They then tell us that in the isolated copper 2 plus ion, the d orbitals are all degenerate. In the complex, they are non-degenerate. What does degenerate and non-degenerate mean in this context? Degeneracy simply means that the orbitals have the same energy, and non-degenerate means they have different energy, right? Explain why the solutions of the two complex ions have different colors. And the reason has to do with the fact that the energy gap, delta E, between the non-degenerate orbitals, are different for the different complexes. And because this energy gap is different, it means that a different frequency or a different wavelength of light will be absorbed for the DD transition. Right? Well, it doesn't necessarily need to be a DD transition, but there will be a different frequency or different wavelength of light being absorbed. And that is why they have different colors, because the color transmitted is complementary to the color absorbed. So we see different colors because the complex absorb different colors. And the reason why they absorb the different colors is because the energy gap between the non-degenerate orbitals are different for the two complexes, right? Then we are told that copper 2 forms a complex ion containing water molecules and ethane dioate ions as ligands. The formula for the complex is given. The ethane dioate ion is a bidentate ligand. What is meant by the term bidentate? So bidentate simply means that the ligand forms two dative bonds, right? Or coordinate bonds. You may refer to it as coordinate bonds. With the central metal atom or ion, right? With the central metal atom or ion. So that is what bidentate means. It forms two dative bonds. You need to be specific that it's a dative bond that's being formed, right? Then they tell us here that there are 3 stereoisomers with the formula shown here. Complete the 3-dimensional diagrams to show these 3 stereoisomers. Right? So if let's draw in this 3-dimensional structure first, right? So we'll have they will all be octahedral complexes. So you would have this series of hashes and wedges. So let's draw in that first. Excuse my drawing a bit in the exam. Try to make it so that you have your 90 degree and 180 degree bond angles, right? And it's not looking so strange as how I had it here. So we have 2 water ligands and 2 ethane dioate ligands, right? So the first way we could arrange the water ligand is we could arrange them so that they stick out like this. Right? And remember, it's the oxygen, it's the lone pair on the oxygen that's bonding to the copper. So I have the oxygen bonded here. So we have the 2 water ligands like this, and then you'll have the ethane dioate ligands, which would connect like this. So we have this, and then we have this, right? This would be your ethane dioate ligands. So we have the water in this situation. We could also have the water ligands like this, next to each other. And you should see immediately that this is a trans orientation of the water ligands, and this is a cis orientation of the water ligands. And then you have, right, and we can have the ethane dioate looking like this, right? So, and this is the cis isomer. And the question becomes, what happens, what is the third isomer? Now the third isomer actually becomes an optical isomer with the cis isomer. We can reflect the cis isomer, and when we reflect the cis isomer in a mirror plane, we get the optical isomer, which we will draw here. If we reflect this in a mirror plane, we'll get water, the water ligand here, and we'll also get a water ligand here, and then you get this arrangement like so, right? And those are your three stereoisomers. So you could have the trans orientation, or what we call the aqua ligands being in the axial positions, and the ethane dioate being in the equatorial positions here. This is the trans stereoisomer. We could then get the cis, where the water ligands are next to each other, and the cis isomer actually gives us our optical isomer, right? We are then asked, or well, we just answered part 3. They say use our answers to show the different types of stereoisomerism found. So, what is the type of isomerism shown with stereoisomer 1 and 2? So, isomer 1 and 2, 1 and 2 shows geometric isomerism, which we know as cis-trans isomerism. And then stereoisomer 2 and 3, right? So 2 and 3 show optical isomerism. In our example here, stereoisomer 1 and 3, these are also geometric isomers as well, right? These are also geometric isomers. So the geometric isomers are 1 and 2 or 1 and 3, but the optical isomers are only 2 and 3. Right? So moving on to part D, it tells us here that a solution contains 3.70 grams of this sodium salt dissolved in 100 cubic centimeters of solution. A 25 cubic centimeter sample of the solution is warmed and oxidized by 0.01 molar acidified permanganate. The redox reaction is shown. Calculate the minimum volume of acidified permanganate needed to oxidize all of the ethane dioate ions in the 25 cubic centimeter sample. Right, so we should know that the concentration on 1,000 multiplied by volume gives you the number of moles. Right, so we need to work out the number of moles of permanganate required. So first we need to work out the number of moles of ethane dioate. Right, now the number of moles of ethane dioate is 2 times the number of moles of the sodium salt, because the sodium salt will dissolve, and when that breaks up, we have 2 moles of ethane dioate inside here. So the number of moles of the sodium salt is 3.70 divided by 321.5, which is 0.0115 moles, right? This means that the number of moles of C2O42 minus is 0.0115 by 2, which is 0.0230 moles, right? Now, this is in the 100 cubic centimeter solution. We took out 25 cubic centimeters in our sample. So the number of moles that are actively being used in the titration would actually be 0.0230 divided by 4, right? Because 100 divided by 25 is 4. So 0.023 divided by 4 is 5.75 by 10 to the minus 3 moles of ethane dioate. And the mole ratio of ethane dioate to manganate is 5 to 2. Therefore, if we divide by 5, we get 2/5. So it's a 1 to 2/5 ratio. So the number of moles of permanganate would be equal to 2/5 by 5.75 by 10 to the minus 3, which is 2.3 by 10 to the minus 3. And then we substitute this for n here, and then we could solve for volume. So it becomes 2.3 by 10 to the minus 3 multiplied by 1,000 divided by the concentration, which is 0.01, and that gives you 230 230 cubic centimeters. Right, 230 cubic centimeters. Now, when working this question out in the exam, try to avoid this rounding error that I made here. I approximated my answer. Remember, a good practice is only approximate your final answer. So evaluate all of these things directly in your calculator. Don't round off so soon as I did here. Right? Don't do that. Just evaluate everything directly in your calculator, and you should actually get the more accurate answer of 230.25 cubic centimeters. Right? Good. Then they tell us copper 2 nitrate and barium nitrate both decompose when heated, but copper 2 nitrate decomposes at a lower temperature than barium nitrate. Suggests a reason for this difference. So because the copper 2 nitrate is decomposing at a lower temperature, it means the copper 2 nitrate is less thermally stable. What does this mean? This think back to your knowledge on the stability of the group 2 nitrates and carbonates. Right? What this means is that the copper 2 ion is a smaller ion. Right? Cu2 plus is smaller than Ba2 plus. Because it's a smaller ion, its polarizing effect is greater. So it polarizes or distorts, it polarizes or distorts the nitrate electron cloud more. Therefore, this distortion, because it's a smaller ion and it's more polarizing, this distortion weakens the bonds. Right? Weakens the bonds in the nitrate. Therefore, lower decomposition temperature. Right? And that is question number 5. Moving on to question number 6, which is also based on transition metal chemistry. We are told here now an aqueous solution of cobalt 2 chloride is pink due to the presence of this cobalt complex. Complete table 6 to describe what is observed when the named reagent is added to an aqueous solution of cobalt 2 chloride. And we have to fill out the color and the state. So when sodium hydroxide is added, what you actually get, you can get two things. They did not specify if you add excess sodium hydroxide or not. You could get a blue or a pink solid, blue or pink. And in both cases, it's a solid product. When you add excess HCl, you get a blue solution, and it's aqueous, right? It's not liquid, it's aqueous, right? And they ask us here to write an equation for the reaction between the cobalt complex, the hexa-aqua cobalt 2 complex, and sodium hydroxide. So when you have, so there are two things that could happen here, right, to be really exact. When you have, so I have CO, H2O6, 2 plus, this could combine with hydroxide ions to form COOH, H2O5, 2 plus, plus H2O, right? And this here is the blue solid, and this occurs when you have, when the sodium hydroxide is not in excess. So if you actually do this reaction, you would see actual little flakes of blue solid that eventually turn pink upon exposure to excess hydroxide ions. And when you have excess hydroxide ions, the reaction that occurs is as follows. You have COH2O6 2 plus 2OH minus to give COOH2 H2O4 plus 2H2O, and it might be useful here to actually include your state symbols. So this is aqueous, aqueous, solid, liquid. Likewise, here would be aqueous, aqueous, solid, liquid, right? And this is what gives rise to the pink solid. Good? And then they similarly ask for an equation where we have excess concentrated HCl. So the excess concentrated HCl we have COH2O6 2 plus 4Cl minus to give COCl4 2 minus plus 6H2O. Right? Good. Then they ask us to define the term stability constant. Now, what is the stability constant? It is the equilibrium constant for the formation of a complex ion from its constituent ions in a solvent at a given temperature, right? Always at a given temperature. Good. Then they ask us to write an expression for the stability constant of the cobalt, of this hexaamine cobalt 2 complex, right? Now, how is this complex formed? This complex, as we could see, is formed from taking COH2O6 2 plus reacting it with 6 molecules of ammonia to give this complex plus 6 molecules of water. Now, we don't include water in our K-stab expression, so it would become the product, which is CONH362 plus all over the concentration of COH2O6 2 plus by ammonia to the power 6. And what would be our units? So we have mole per cubic decimeter all over mole per cubic decimeter by mole per cubic decimeter to the power 6, which is mole 6 dm to the minus 18. This cancels, and when we bring this to the numerator, it becomes positive. So the unit is mole to the minus 6 dm to the 18. Good? Then we are told the numerical value of the stability constant of the complex is this, 7.7 by 10 to the 4. In an aqueous solution, the concentration of the ammonia complex is that, and the concentration of ammonia is that at equilibrium. Calculate the concentration of the water complex, right, in the solution. It's just a matter of making the water the subject of the formula. So it would mean that the concentration of H2O6 2 plus is the K-stab value, which is 7.7. Actually, no, it would be the concentration of the ammonia ligand, which is 0.0740, all over the K-stab value, which is 7.7 by 10 to the 4, multiplied by ammonia, 0.48 to the power 6. And this should give 7.86 by 10 to the minus 5 moles per cubic decimeter. Good, and that is question number 6. Moving on to question number 7. Right, so question number 7 now, we begin to look at the organic chemistry questions, and they give us here the structural and displayed formula of 3 aromatic compounds, which are shown here. They ask us to compare the relative acidities of A, B, and C. So we should see here that B is a phenol, A is a carboxylic acid, and C is a chloro-substituted carboxylic acid. So we should be able to immediately tell, we should know that the acidity, if we compare alcohols, phenols, carboxylic acids, we should know that carboxylic acids are the most acidic, then phenols, then alcohols. Right? And then we should also know that when we have chlorine or halogen substituted carboxylic acids, they tend to be more acidic as well. So the most acidic species here would be C because of this. Then we would have A, and then we would have B. Now, how do we explain this ranking or this relative acidity? So what you need to remember, acid strength depends on 2 factors: the polarity of the OH bond and the stability of your conjugate base, of the conjugate base that's formed. Right? Now, if the conjugate base is very stable, what does that mean? So let us consider, let's just take, for instance, let's take a phenol, right? Just to illustrate the idea. The phenol, when it acts as an acid, it will form the phenoxide ion. The phenoxide ion becomes your conjugate base. Right, and this phenoxide ion becomes our conjugate base. Now, what we mean by the stability of the conjugate base. If the conjugate base is stable, it means it does not readily recombine with an H plus ion to form back the parent compound. If it does that, then we are reducing the acidity because you have less free H plus ions in solution. So the more stable the conjugate base, it means it's more quote-unquote unreactive. If the conjugate base is unstable, it's very reactive and it readily picks up back the H plus to form back the parent compound. We know that in the case of the phenoxide ion, the oxygen lone pair is delocalized into the ring, and this increases the stability of the conjugate base, the stability of the phenoxide ion, and it means that these lone pairs on the oxygen are not readily available to pick back up a proton. So we have to apply these two ideas to the ranking of C, A, and B. Now we should know that the polarity of the OH bond is the greatest in C because of the electronegative chlorine atom. So in C, you would say that we have electronegative Cl, which has an electron withdrawing effect. Right? There's an electron withdrawing effect. It pulls electron density away from the OH bond, right? And this polarizes the OH bond. And this OH bond will actually be the most polar, right? So most polar OH bond, therefore it's the weakest of the OH bond. If it's a weak bond, it's easier to break, so the proton could become free in solution. The anion as well, the carboxylate ion that we have, is also stabilized due to conjugation within this carboxylate system, right? So the anion is also most stabilized. The anion readily stabilized. And the anion here it essentially means the conjugate base. It's very stable, right? So it's a weak conjugate base. Right, a weak conjugate base. Then we could also look at in the case of A, we have the electron withdrawing effects here of the carbonyl group, because the carbonyl group is electron withdrawing, so it pulls electron density away. The OH bond is polar. It is not as polar as C, and the conjugate base is not as stable as C. And in the case of B, the benzene ring is not as electron withdrawing as the halogen atoms were. So the polarity of the OH bond here is the least, it's the least polar of the three, and the conjugate base that is formed is also the least stable. But mind you, it is still a stable conjugate base because we will have the localization of the oxygen lone pair into the ring in benzene. So again, in summary, you always explain your response with relative acidities in terms of these two things: the polarity of the OH bond and the stability of the conjugate base. In C, you have that electronegative chlorine. It's electron withdrawing. It polarizes the OH bond. It's the weakest bond. And the anion is stabilized due to conjugation within the carboxylate system. And then in B as well, you would say that the benzene ring is not as electron withdrawing and the lone pair is stabilized into the ring. So you have to make comments based on these two things: polarity of the OH bond, stability of the conjugate base, in explaining relative acidity. Likewise, when you do relative basicity, the base strength simply depends on the availability of lone pairs for protonation, right? So good, so that's part A. Part B, they tell us methylbenzene can be made from benzene by electrophilic substitution. Specifically, it's electrophilic aromatic substitution. Identify the compound that reacts with benzene to form methylbenzene and identify the catalyst, right? So this is a Friedel-Crafts alkylation reaction. So the compound that we will react is chloromethane, which is CH3Cl, and the catalyst will be a halogen carrier, AlCl3. Right? Then we are asked to show the first step to show the generation of the CH3 plus electrophile. So an reaction, an equation for this reaction is that AlCl3 reacts with CHCl to give CH3 plus and AlCl4 minus. Now, I'll just demonstrate this. You don't need to know this for the exam, but because the next part of the question, I imagine, is going to ask about a mechanism, yes. I'll just introduce the mechanism that unfolds here. But you don't need to know this. So I'll put this, not examinable. You don't need to know this, but this is just what happens here mechanistically. What happens is you have this is Cl, the chloromethane, and then you have AlCl3. We should know that aluminium could expand its octet, right? And we have a lone pair here on the chlorine. This lone pair forms a bond here with the aluminium, so we get this system forming AlCl3. Right? This picks up a negative charge, and this picks up a positive charge. What happens is that this bond breaks heterolytically, and you end up with your electrophile CH3 plus and your AlCl4 minus. So this is mechanistically how these things form. Again, you don't need to know this for the exam. Right? Then they say, describe the mechanism for the reaction between benzene and the CH3 plus electrophile, include all relevant curly arrows and charges. So this is extremely important here. Your first arrow has to come from the aromatic ring itself, from the pi electron. So from the circle to the carbon, and it's a full arrow, right? So from the circle to the carbon, and you then have to show the formation of this intermediate. Now you could attach the CH3 at any position. I'll choose to attach it here, and you also have H. And this carbon that contains CH3 and H is now an sp3 hybridized carbon. The other carbons in the benzene ring retain their sp2 hybridization. So the positive charge is actually spread away from this sp3 carbon. So you put your positive charge in the intermediate away from this sp3 carbon, and notice the circle I have also is not drawn up to the sp3 carbon. It starts here and it starts here. And then what happens is this proton is lost into the ring, and you form your compound methylbenzene and H+. And this is the mechanism that they expect you to produce in the exam. Now, if you are very keen, you should recognize that what you really get is HCl at the end of this reaction. You may be asking yourself, how is the HCl actually formed? So again, I will discuss how the HCl is actually formed, but you don't need to know this. This is not examinable for the exam as well. It actually has to do with this species that we would have formed here, this AlCl4 minus. Right? What actually happens in this step is that the proton is not just lost. The AlCl4 minus actually abstracts the proton. So what you actually have is Cl, AlCl3, and you have a minus charge here, and you have lone pairs here on this chlorine atom. What happens is that this bond breaks, and a lone pair moves onto the chlorine. And a lone pair from the chlorine actually comes in and abstracts this proton, and then this proton bond breaks. So at the end, what you really get is your methylbenzene, HCl, and AlCl3. And remember, it's a catalyst. This is how we regenerate the catalyst. So again, this is not required for the exam. The first step I've shown is all that is required. This is just to give some more detail as to what a more accurate representation of what occurs in the mechanism, right? And that is the mechanism for the reaction. Good. Then they say here, identify a suitable reagent to oxidize methylbenzene to benzoic acid. Write an equation for this reaction using O to represent one atom of oxygen. So what is the reagent for the oxidation? So to oxidize it, we have to use alkaline conditions of potassium permanganate, and we heat, right? This is what we use, alkaline KMNO4 and heat. And the equation is that C6H5 CH3 combines with oxygen to give C6H5 CO2H plus water. Right, now notice we are adding 3 oxygens into the thing, into the species, so we just put a 3 here and everything balances. Right? Good. Part 5. Methylbenzene and benzoic acid are both nitrated with a mixture of concentrated nitric and sulfuric acid to give mononitrated products. Mononitrated products, the structural formula are as shown. Draw the structure of these products. So we want methylbenzene. So methylbenzene, nitration, and they tell us that benzoic acid, nitration as well. Right, so CO2H. What will be our products? Now, what you need to remember, and this is a good rule to remember, it's a general rule that works. Saturated substituents on the benzene ring tend to be 2,4,6 directing. So syraturated substituents are 2,4,6 directing. Sometimes you may hear this referred to as ortho para directing. And then we have unsaturated substituents tend to be 3,5 directing. And you may also hear this referred to as meta directors. So this methylbenzene, the methylbenzene is a 2,4,6 directing group, or a orthopara director. So it means it will direct the incoming nitro group to position 2. So this is 2, 3, 4, 5, 6. This is position 1. Position 1 is sometimes called the ipso position. So this methyl group will direct to positions 2 or to position 4. So you could draw either one, the nitro group at position 2 or the nitro group at position 4. In reality, the nitro group at position 4 will actually be the major product of the reaction. It has to do with steric hindrance. The incoming nitro group will experience some steric hindrance at position 2. So the 4 product actually forms in preference. And then likewise here, the carboxylic acid group is unsaturated. So it's a 3,5 or meta-directing group. So we would expect to get this as our product. 1, 2, 3, the nitro group will add here, right? And it's mononitration, so we just do one product, right? And that's our answer for this part of the question, right? Right, so in part C now, we are looking at this reaction scheme here. So they ask us here to describe the reagents and conditions to produce this salt from the phenylamine compound in reaction 2. So we should know that it's, so if we draw out what's happening, we have this that's going to this, and then this is going to this, N triple bond N Cl minus N plus, right? That is what this is. So what is the reagents for this conversion? It is sodium nitrite and concentrated HCl, and this generates the species HNO2, which is what actually carries out the reaction. And the conditions is temperature less than 10 degrees C. Anything above this and this reaction could actually become explosive, right? Then they ask us to describe how we could get this species from this. So what they are talking is this conversion. So we are converting it back to a phenol, right? And to do this, all what we do is we heat, right? Now we have to heat it in aqueous solution. So heat an aqueous solution, which means in water. And obviously now we should specify that the temperature has to be greater than 10 degrees. And you just heat it and you get this phenol product. Good. Then they say, draw the structure of the di-molecule Y formed when the salt here, this, combines with CH3C6H4OH. So these two things are combining together. These two things are combining together to give the final structure, and they want us to state the conditions required here. Now, what are the conditions here? So this diazotization reaction, we would actually need sodium hydroxide, and you would need a fairly cold temperature. So we could say temperature less than 10 degrees C here. Now, what is going to happen? So we are going to get this N double bond N that's going to form, right? So what's going to happen is we are going to, so if we consider this part of the benzene ring, we will now have N double bond N, which is the azo group, and this is going to bond with the phenol. And where would this bond, right? So it has to do with which one is a stronger orthopara directing group. So what would happen, I think, they wouldn't necessarily penalize you in the exam for this, but you would get this as the compound. So I will put my CH3 here, well, my OH here, and my CH3 here, right? This is the compound that we form, and this is the azo link here, right? Good. And that is question number 7, right? So now question number 8. So they say when answering this question, it should be assumed that all the hydrogen atoms in the benzene ring gives an unsplit peak at delta 7.2 in the proton NMR spectrum. Okay. Good, and they tell us that if structures of 5 isomeric ketones P, Q, R, S, and T are given, identify all the chiral carbons on the structures above, label each chiral carbon with an asterisk. So at this level, you are expected to know that a chiral carbon is just one that's bonded to 4 different groups. So immediately, none of the carbons in the C6H5 should be considered, right? C6H5. This is bonded to 2 hydrogens, so we can't consider that. We can't consider that. This carbon is bonded to 2 methyl groups, so we can't consider this. We can't consider this. We can't consider this. Likewise, this is bonded to 2 hydrogens, not bonded to 4 groups. So the only answer is T has to have the chiral carbon, and actually the chiral carbon is right here. It's bonded to the C6H5 group, a proton, a CH3 group, and then this. Right? So that's your chiral carbon. The carbon shown there. Let me just clear this up so it could be more visible. I'll just erase all of this, right? So it's this carbon right here. Good. Then they say the proton NMR spectrum of one of the 5 isomers is shown. Identify which of the compounds give its spectrum. Draw the displayed formula you have identified. Identify the protons responsible for the peaks on the structure you have drawn. So we know that this peak here is due to the aromatic protons on the benzene ring. What we have to look for is we have a quartet and we have a triplet. So this is a quartet peak and this is a triplet peak. What does this mean? By the n+1 rule, it means that the protons giving rise to this peak have to be adjacent to some CH2 group. And it also means that the quartet is adjacent. The protons giving rise to the quartet have to be adjacent to something that has 3 protons in it. So this means that we have a CH3 CH2 functional group, right? So the quartet and the triplet implies CH3 CH2, right? So this CH2 would give rise to the quartet because we have 3 + 1, 4, and then this CH3 gives rise to the triplet because we have 2 + 1, 3. So CH3, CH2. It rules out P, it rules out S, and it rules out T. So now the question becomes, is it Q or R? If we look carefully at the structure of Q, we have CH2, CH3, yes, but it's the order in which this is bonded. We have the C6H5, then we have C double bond O, then we have CH2, CH2, and CH3. So this CH3 would indeed give a triplet peak. This CH2, on the other hand, would give a triplet peak as well. So we should see two triplets if it was Q. And this CH2 here would actually give 3, 4, 5. 5 plus 1 is 6. It will give something known as a sextet, which we will simply call a multiplet, right? So it cannot be Q. It has to be R by the process of elimination. And if we draw in the protons for R, if we draw in the displayed structure of R, we should see this. This, we have CH2. Oh, my bad. We have CH2. Right, CH2. C double bond O. CH2 and CH3, and rightfully so, this CH3 is the triplet peak at delta 1.0. This CH2 is the quartet peak at delta 2.5, and this is the singlet peak here at 3.7. Good, so that's how you could figure this out from just elimination. Right? Then they say name the splitting pattern of the peak at delta 3.7. It's a singlet, and explain why it has this pattern. No adjacent protons. No adjacent protons on the carbon, or no neighboring protons on the carbon, or no adjacent hydrogen atoms on the carbon. Right? Good. Then they tell us, choose from the letters P, Q, R, and S, P, Q, R, S, and T to identify the two compounds that each have a doublet peak in the proton NMR spectrum. Right, so a doublet peak. So if we have a doublet peak, it means it's a proton that's adjacent to 2, right? That's adjacent to 1, sorry, right? There's one adjacent proton. So which species here would give a doublet peak? It cannot be, well, it cannot be R, and it cannot be Q. So R and Q are out. Can it be S? Right? It cannot be S because S, this will give a singlet, this will give a triplet, this will give a triplet, and this will give a singlet. Right? So it cannot be S. If we look at T, will T give a doublet peak? The answer is yes. If we draw the structure of T, C6H5, we have CH, CH3, CO, CH3. This proton here, these CH3 protons, CHH, if I draw them out, it's 1, 2, 3. They will couple with this proton here to give a doublet peak. So T has to be an option, and let us also consider P. We have C6H5 bonded to C double bond O. Right, this bonded to C double bond O. This is then bonded to CH, and then this is bonded to a methyl group here and a methyl group here. So what is going to happen? Now, what we should recognize is that these methyl groups are actually equivalent protons, right? They are equivalent protons. So let me just redraw P with a little bit more clearer. So we have the benzene ring, C double bond O, CH, CH3, CH3. So what will happen is that these methyl groups will couple with this proton to give a doublet. So the two doublet containing species will be P and T. Right, so this will be P and T. The compound with only 3 peaks in its NMR spectrum. Well, we know it can't be R. It can't be Q because Q will give a peak here. We'll get a peak for this, this, and this. It can't be T because we'll get one peak here. We'll get one peak here, one peak here, and one peak here, so that's 4 peaks. This will give one peak, one peak, one peak, and this will give 4 peaks. So by elimination, it has to be P. But what are the 3 peaks in P? So this, the benzene ring gives one peak. This proton will give one peak, and then these methyls are in the same proton environment. They are equivalent protons because they are both bonded to a carbon, bonded to a H, bonded to C double bond O C6H5. So they are bonded to the same type of carbon. So they are in the same chemical environment. So this will also give and this will give a single peak. Right? So this proton will actually give you the quartet, and this will give you a doublet. Right? So the answer is P for the compound with 3 peaks. Good. A suitable solvent that could be used for obtaining the spectrum. So in NMR, proton NMR, we use a deuterated solvent, so CdCl3, or you could say in words deuterated chloromethane. Right? Then they ask us the proton NMR spectrum of compound T is compared in the presence of D2O and in the absence of D2O. Describe any difference between the two spectra. Explain your answer. Now D2O is really used for the identification of OH and NH peaks. We have neither of those in our structure, so there would be no change in the spectra, no change. And the reason is we have no labile protons, right? And what is labile? Labile proton simply means protons that can exchange with D2O, right? That's what we mean. So that is what would happen here. Right, and then part F tells us to deduce the number of peaks in the carbon-13 NMR spectrum of the compounds. Now, how do we figure out carbon-13 NMR spectra? What we have to consider is basically symmetry within the molecule. Symmetry within the molecule gives us an idea of which carbons are equivalent to each other or not. So, if we look at this compound here, we can see now there is a sort of symmetry line here with the benzene ring, in that this carbon is equivalent to this carbon is equivalent to this carbon. So this is one peak, peak number 2, peak number 3, peak number 4, peak number 5. So 1, 2, 3, right, so this is peak 1, peak 2, right, sorry, this is 1 peak, 2 peaks, 3 peaks, 4 peaks, 5 peaks, and 6 peaks, so we get 6 peaks, right? If we look at this structure, we have a perfect mirror line here. So it means that this carbon is identical to this carbon, so this is 1 peak. It also means that this carbon is equivalent to this carbon, so that's 2 peaks. This carbon is equivalent to this carbon, so that's 3 peaks. And then we have this carbon, which gives a 4th peak, and this carbon, which gives a 5th peak, so we get 5. Right? If we look at this structure here, we also have a mirror line here. This carbon is equivalent to this carbon, so that's 1. This carbon is equivalent to this carbon, so that's 2. 3, and 4. So we get 4 peaks. And in this structure, 1,4-dimethylbenzene, we notice we have 2 mirror lines in this case. So it means that this carbon is equivalent to this carbon, so that's 1 peak. And it also means that this carbon is equivalent to this carbon, so that's 2 peaks. But something special happens with these 4 carbons. This carbon is equivalent to this carbon, but it is also equivalent to this carbon. The same could be said about this carbon. This carbon is equivalent to this carbon, but also equivalent to this carbon. And what we actually find is that all 4 of these carbons are chemically equivalent to each other. So all 4 of these carbons gives a 3rd peak. So we get 3 peaks in total. So with these structures, it's really a good idea to practice as much as you can, and it really has to do with symmetry. Once you understand the concept of symmetry, you will find no difficulty with the question. Right, and now we move on to question 9, the final question on the paper, which deals with amino acids. Tyrosine and lysine are shown, and they are naturally occurring amino acids found in proteins, right? They tell us that the isoelectric point of lysine is 9.47, right? Draw the structure of lysine at the stated pH in the boxes below. So remember the general structure of amino acid. You have a carbon bonded to an acid group bonded to an amino group, bonded to hydrogen, and bonded to an R group. So in this case, this here is our R group, and this here is also our R group, right? Because this is our proton coming out here. Good. Now the isoelectric point of lysine is 9.47. What do we mean by the isoelectric point? This is the pH, so this is a pH at which the species is neutral, right? And what do we mean by that? We mean that it exists as a Zwitter ion, right? So let us consider the Zwitter ionic state of lysine first and foremost. Now, the Zwitter ionic state means that you must have equal number of positive and negative charges. It should be apparent that the carboxylic group will become the carboxylate ion. Now, the amino groups are basic. The question is, we could only protonate one of the amino groups. Which amino group do we protonate? And the question has to be considered, which amino group is more basic? That is what will help us answer the question. So which of these two amino groups is the terminal amino group on the side chain of lysine more basic or less basic than this amino group, which is what we call the alpha amino group, right? So it turns out that this group is considerably more basic than this group. And again, remember, base strength has to do with the availability of the lone pair on the nitrogen here to pick up that proton. This NH2 group is very close to this electron withdrawing carbonyl. So it pulls electron density away, right? Versus this entire alkyl chain, which is electron releasing. It releases electron density onto the nitrogen atom, and it makes the lone pair on this nitrogen much more available. So we find that this terminal NH2 group is considerably more basic than the alpha amino group. So it is this NH2 group that is preferentially protonated in lysine. So at pH 9.47, our structure would look like this. We would expect a structure like this. My bad. We would expect a structure like this. So 1, 2, 3, 4, 5, NH2, COO minus, right? It's equal number of positive and negative charges. 1, 2, 3, 4 carbons in between. 1, 2, 3, 4 carbons in between, right? Good. What happens at pH 7? So at pH 9.47, lysine is quote-unquote neutral. Therefore, a pH of 7 will actually represent an acidic environment for lysine. So what would happen in our acidic environment? In our acidic environment, we would actually protonate the carboxylic group. So at pH 7, you would just have the terminal amino group protonated, right? Right, 1, 2, 3, 4, 5, COOH, NH2, and then at pH 12 you have basic pH. What would happen is you would end up having the carboxylic group alone deprotonated, and the NH3 plus will be neutral. So you will have NH2, 1, 2, 3, 4, NH2, COO minus. So those are the three species you would have at the various pHs, right? Then they tell us when ethanoic acid is treated with PCl5, compound D is formed. So compound D, what is compound D? And they want us to know the structure of compound D. So ethanoic acid with PCl5, PCl5 is a chlorinating agent. We will get ethanyl chloride, which is this. Right? When D is added to tyrosine, two different isomeric products, E and F, are formed. E has an ester linkage, F does not. Draw the structure D, E, and F in the box. So we know that we'll get a condensation type reaction happening. So E has the ester linkage. So the ester linkage has to form with this group here. What will happen? You will get COCl. You would lose HCl, and you will get COO. Right? So that is what will happen here. Why can't we do it on the carboxylic group? If you add the ethanoyl chloride to this end, you actually will not get an ester. You will get something called the anhydride. You get this thing, which is called an anhydride, right? You don't get the ester. So that's why you can't do the reaction on this end of the molecule. So the ester, the phenyl ester, will look like this. O, right? This, bam bam, NH2, and then we have COOH. And then they say F does not have the ester linkage, right? What would happen here? So what would actually happen based on the confines of the syllabus again, you would actually form NH, you would form an amide here at the amino group. So this amino group will actually react to form an amide. So you would get a structure that looks like this. OH, bam, NH, COCH3, and you get COOH. So those are the three structures that you form, right? And of course you get HCl as byproducts in each of these, right? Good. Then they say complete table 9.1 by drawing in the structure of the organic product formed when tyrosine reacts with each named reagent. Ignore the directing effect of this substituent. So let me just draw back in here what will happen with tyrosine when we react with an excess of Br2. So the structure of tyrosine is this, right? We have OH and we have NH2 COOH. What we should know is that this is essentially a phenol functional group. Phenols react with bromine, and bromination occur at the 2, 4, 6 positions. So bromine will occur at the 2 and 6 positions here, or the ortho positions, right? When we react with an excess of sodium hydroxide. So what happens when we have an excess of sodium hydroxide? The phenol is basic, the OH of the phenol is basic, and the OH of the acid is basic. So you would get the corresponding anionic species form. So you get O minus forming here. NH2 is a basic group, so it will not react with a base, and you get O minus here. And of course you have the counter ions, Na plus, Na plus. And then they say an excess of nitric acid. So what will happen when we have an excess of nitric acid? Now they did not specify whether the nitric acid was concentrated or dilute, right? So either products here would work. Now again, you have a phenol ring. If you have dilute nitric acid, you get a mononitration onto the ring. If it is concentrated nitric acid, however, what will happen is, so this is a dilute nitric acid, you get mononitration on the ring. If it's concentrated nitric acid, you get nitrations at both the 2 and 6 positions, right? So you could have drawn either product and you should have been fine, right? Good. Then they say a mixture of tyrosine and lysine can be separated by thin layer chromatography, TLC. Under certain conditions, the RF value of lysine is 0.14, the RF value of tyrosine is 0.45. What is meant by the RF value? It's the distance the solute travels. So the distance solute travels over the distance from the baseline to the solvent front, which is essentially the distance the solvent travels, or distance of solvent front. And this is suggests an explanation for the RF, for the difference in RF values. Now the RF of lysine is much smaller than the RF of tyrosine. It means tyrosine travels further along the column. What does that mean? It means that therefore tyrosine is more soluble in the mobile phase because it travels further down the column. So more soluble in mobile phase. Or you could make the reverse argument, lysine is less soluble in the mobile phase, right? Or you could consider this by saying that lysine is more strongly withheld, or more strongly attracted to the stationary phase than tyrosine. Or conversely, tyrosine is are less attracted or less withheld by the stationary phase. Right, so either one of these gives an explanation into the RF values, and that is the end of question 9, and that is the end of the paper. So it wasn't a particularly difficult paper, I would say, but there are definitely areas, especially in the calculations, where you could have made little errors. Little errors like in this question, as well as in knowing which amino group to protonate, etc., which may have made the paper a little bit more challenging than it actually seemed. But all in all, I would say this was a pretty good paper. Again, an E for this paper was 57, so not too bad. So hopefully this work-through has benefited some of you all. If you have any further questions, just leave them in the comment section. And if you want any more papers done, also leave them in the comment section, and I will try to do them when I can. And all the best in your upcoming exams. Hope this was helpful to some of you all, and I will see you all in the next video.